I think one of the most amazing, beautiful concepts from the modern AI world are embeddings. They're extremely helpful. And when you know how embeddings work, when you know how to use them, you can find all sort of interesting ways to take advantage of them. Okay, so in today's video, I want to show you how you can create your own embeddings from scratch. Okay, how you can implement a very simple neural network for you to understand how to create these embeddings in the first place. Now, I'm not going to be using any complex structures. I'm not going to be using transformers. There are multiple ways to generate these embeddings. I'm just going to use a simple neural network, okay? And I'm going to show you line by line how I create those embeddings for images. Now, if you do not have an idea of what I'm talking about here, let me show you here the Cohere playground. So in this playground, Cohere has a way for you to write some text and generate embeddings for that text. And what's really cool about this playground is that Cohere gives you a visualization of these embeddings in space. Now, as a reminder, an embedding is just a vector, an array of floating point numbers. That's it, a bunch of numbers. So if I have an embedding of 4,000 numbers, those represent coordinates in multi-dimensional space, okay? So I like to think about embeddings like latitude and longitude, okay? Where with those two coordinates, you can place a point anywhere in the world. It's the same idea with embeddings, but instead of working in 2 dimensions, they work in multi-dimensions. So it's really a little bit hard to reason about them with more than 2 dimensions. Anyway, what you see here on the screen is the Cohere playground, and I typed 6 words off camera, 4 of those words. So I have bananas, apples, rice. Those 3 words represent food, obviously. They are food concepts. And I have camera, photography, and tripod, which again, they represent some sort of like photography related concepts. And I'm gonna generate embeddings for this, okay? So I'm gonna click on this run button here, and Cohere is going to compute. It's gonna use an embedding model to compute the coordinates of these concepts, to place these concepts in the world, okay? And then it's gonna give me a 2D representation here. So obviously it's reducing the dimensionality of those coordinates, and it's just giving me a 2D representation here. Now, notice something super cool, which is I have 3 concepts down here, and I have 3 more concepts up here. So it's like a small cluster here. Now, if we look at it, you can see photography and tripod, they are close together versus rice and apple, which are closer together. And that is one of the main characteristics of an embedding. Like, similar concepts are going to have coordinates in this multidimensional space that are close to each other. And separate concepts that don't look alike, they are going to have coordinates pointing to directions that are very, very far apart. That's the main advantage of this embedding. So before I show you the code and before we run and build this embedding thing, let me tell you something else. Why are these embeddings important? Why do you really care? Well, you've heard about RAG applications, for example. So when we're using RAG application, the whole idea is to provide some context for a model to answer a question. So imagine a person is asking a question about a specific document that you have stored, okay? So the idea is you're gonna get that question from the user. You are going to find related documents in your database of documents, and you're gonna get that document, the document that better resembles or is that the most similar to the question, give those 2 pieces of information to a large language model and ask the model, can you please ask this question using this document? But the key here is, how do you find related documents to that question? And the answer is through embeddings, because you can generate an embedding for a question, and you are going to store embeddings for all of your documents. So if you have that database of embeddings, now you can use a concept which is called similarity to find which of those embeddings are the most similar to the query provided by the user. And similarity is just distance. So we can compute the distance between those two coordinates or two set of vectors, which are just coordinates. And the closer they are, the more related they are. Okay? That's the idea. That's the power of these embeddings. Now, today, I'm going to build this from scratch, and hopefully we're going to learn something together. Now, this is a little diagram that I put here to show you what the structure of the network that I'm going to build will look like. Okay, and it's going to be very simple. I promise. It looks more complex than what it actually is. Okay, so I'm going to be using this paper. It's called Dimensionality Reduction by Learning and Invariant Mapping. And it's an old paper, okay? It's a paper from 2005, and one of the authors is Yann LeCun. I hope you know who he is. He's one of my idols here. All right, so in this paper, Yann and et al., they propose a function to learn how to reduce the dimensionality of a vector. I'm gonna be using this paper to implement that loss function, which is called the contrastive loss function. Let me just find it here. So we can, what is the loss function here? Okay, there we go. So the loss function is right here. I think this is page, whatever, you can find it. But this is the loss function that I'm going to implement. And you'll see in a second what it means and why it works, etc. But I'm gonna implement this loss function to learn how to generate embeddings for images. Now, not any images because I need to keep this very simple, but I'm gonna be using the MNIST data set, which is just a data set of handwritten digits. So you're gonna get images like these 3 and these 7 that I have here on my screen, right? So that is a handwritten 3 and a handwritten 7. And what I want to do is I want to be able to generate embeddings for those images. And if I do that correctly, I'm gonna end up with a model that, given a handwritten digit, is going to generate coordinates for that handwritten digit that will fall in this world, multi-dimensional world. A coordinate generated for the number 3 should be closer to any other coordinates for any other handwritten digit that represents number 3. And if I pass number 3 and number 7, those coordinates, those embeddings should be very, very far apart. That is my goal. Now, how am I gonna do this? How am I gonna get to this point? Well, I'm gonna use a concept that's called a Siamese network. And you can find more information about Siamese networks online. But the idea with a Siamese network is that I'm gonna create a neural network with 2 heads. So there are gonna be 2 inputs. Instead of a single input that you're probably used to for a neural network, I'm gonna be passing 2 different inputs. And each of those inputs are going to connect, are gonna lead to a trunk or a body, if you will, which is this, what I'm calling here the network. And that network is the neural network that's going to generate the embedding. Like the output of that neural network is going to be the embedding that we want to learn, right? So that is sort of like the main work is gonna happen through this network here. And again, I'm just displaying here the body, and you can see that I'm using dotted lines, and I have a node that says the 2 twins. I'm calling them twins because it's a Siamese network. So obviously 2 inputs, there are 2 twins. These 2 twins will share the same weights. So basically what that means is that for representation purposes, I drew them separate, so it makes sense. But in real life, these 2 inputs will be connecting to a single network, a single twin here. And the output are going to be the embeddings of the 2 inputs that I pass. And then I'm gonna have a distance function. And this distance function will compute how far away these 2 embeddings is, okay? Or these 2 embeddings are. And the closer the embeddings are, that indicates that the images are the same. If the distance is large, that indicates that the images are different. So with this Siamese network, let's reason through it really quick. I should be able to get this network to generate coordinates that are correct depending on whether two images are the same or not. So this is the way it's gonna work. I'm gonna take two images, a 3 and a 7, okay? And I'm gonna give these two images at the same time because I have two inputs to the network. And I'm gonna tell the network the ground truth for these two images is going to be a value that's far from 0 because these two images are different. So I want the distance to be large. So I'm gonna tell the network, these two images the distance between them should be large. So these two images are gonna run through the network. At the end of it, I'm gonna compute the distance of the two generated embeddings. If that distance is close, is small, I want a loss function that penalizes my network. Basically, I want the loss function that generates large updates to get these two embeddings to match each other, to get closer to each other. Now, if I pass a 3 and a 3, what I want that distance to result is be close, meaning the distance at the end is gonna be close to 0. It's gonna be very small. And if it's large, if I pass a 3 and a 3, and the resultant distance is large, I want a loss function that, again, penalizes my network by generating large updates. So these two embeddings get close to each other. That's the whole idea here, okay? I'm gonna be providing pairs of images and the network is going to be pushing when those images are the same, pushing them closer when those images are different, pushing them aside. And at the end of it, if I do this enough times, hopefully this network will learn how to generate embeddings that are either close to each other when the images are the same or farther apart when the images are different. So how do we build this? Okay, so let's start with the code. I'm gonna be using Keras, the version 3 of Keras. It's amazing, it's an amazing front end. Particularly for now, I'm gonna be using the TensorFlow backend, but this is the beauty of Keras. When you're using Keras, you can change your backend. Actually, let me make this a little bit bigger so you see better. You can change the backend to JAX or Torch, and nothing else will change in your code. And that is amazing. Keras is just a front end, okay? The actual processing is gonna be done by the backend, but you don't have to worry with the details of that backend. You just need to switch it here. Now, because I'm running on an Mac, so Apple Silicon, JAX and Torch have partial support for that Mac. I'm sure TensorFlow also has partial support. But this network, the one that we're gonna be building, is a little bit custom. It's not your regular network. So there are certain operations that are still not supported by Torch or JAX for Apple Silicon. This code works perfectly fine if you have an NVIDIA GPU or over CPU, okay? You don't need to worry about it. But I want to use my GPU and TensorFlow is well supported. So I'm gonna be using TensorFlow here as the backend. All right, so I'm gonna execute this. That should work. That should initialize Keras there. Awesome. So again, I'm gonna be using the MNIST data set because it's such a popular data set. It already comes not preloaded, but you can load it easily just from using Keras. If you're using Keras, you can just reference it by going dataset.mnist, and then you do the load data, and you know, it's great. It already gives me a train set and a test set. So it's just doing that for me. I don't have to do anything, which is awesome. So I'm gonna load this, and you can see that I'm getting 60,000 images in my train set, okay? 60,000 images of 28 by 28 pixels. So every image is just a square, it's a matrix, 28 pixels, 28 rows, 28 columns. Awesome. And the Y values, so the labels, are just numbers. So it's only one dimension. It's just 60,000 values here. So I'm gonna show you here what this looks like. So I have a little bit of code, a little bit of matplotlib code that is going to display the first 10 images on the train data. Okay, just so you see them. So you can see here, I'm showing the image and I'm showing the label associated with that image. So number 5, this is the image, and it's, you know, the label is number 5 and 0044, etc., etc. So this is sort of like, yeah, it's working. sort of like gives me some confidence that so far the code is working. All right, so here's the thing. I'm gonna go back here. The network that I'm gonna be building is going to be it's gonna have two inputs, and I want to pass to each one of those inputs. This is gonna be a fully connected network, very, very simple. It's not gonna be a convolutional neural network or anything fancy again. Therefore, I'm going to be expecting every single pixel as an input of the images. Now I have, let me pull up my calculator, 28 times 28, because that's the size of the image. If I do that multiplication, I get 784 pixels. Therefore, I'm going to configure my inputs. There are going to be two of them with 784 values. So 784 values are going to come in representing a single image. But the data that I have, it's structured in a different way. The data comes in 3 dimensions, batch size, or not batch size, but how many images, 60,000. And then the second dimension will be how many rows and how many columns. So I'm gonna reshape that to make it 60,000 images of 784 pixels. So you can use to do that. NumPy has a function called reshape, very easy to use. So as you can see here, I'm just gonna reshape my tensor here, and I'm gonna say, hey, keep the first dimension the same, don't touch it. That's what the -1 or the -1 means. And then change the other 2 dimensions to 784, just an array with 784 positions. And hold and behold, when I execute this, that's what it does. So now you can see the shape is 60,000 by 784. So now I have all of my pixels, all of my images are just a stream of pixels. That's it. That's what I want. So it's easier for me to provide this information to my network when I build it. All right, cool. Something else that we gotta do. I'm going to display here. I'm gonna create a new cell really quick. And I'm gonna display the first image that we have. Okay, so this is the first image of the train set. So look at this. There are a bunch of zeros and there are a bunch of numbers that are not zeros. These are pixel values. This is a black and white image, and every pixel is represented with a value between 0 and 255. 0 means black, no light. 255 means pure white. Okay, so full light. So when you get something like 26, that's gray, closer to 0, but it's not super dark, it's lighter gray, right? And 253 is almost white. Neural networks don't like to work with numbers that have a very large range. So they would not like to work with numbers that go from 0 to 255. So they are gonna work better if we give them numbers that stay within a very small range. So what I'm going to do right now is I'm gonna normalize this image. Normalization basically takes these values and squeeze them into a smaller range. In this case, that range is gonna be 0 to 1. So I want all of the pixel values to be between 0 and 1. All right, so I'm gonna go back here. I'm gonna remove this. This is the formula for normalization that I'm going to use. It's a very simple one. It's called min-max scaling. And basically, the way it works is I'm gonna get a pixel value and subtract the minimum of all of the pixel values. Now, the minimum we know is 0. That's the minimum value. So whatever the number is minus 0, that's just x. Divided by the maximum of all of the pixel values, we know that's gonna be 255, minus 0. So this is going to simplify to every pixel is gonna be equal to that pixel divided by 255. That's it. That's how you squeeze all of the values. So there is an explanation here in the notebook if you want to read it in the code. I'm just gonna apply that transformation. As you can see, I'm just dividing the whole matrix divided by 255. That's gonna change all of the numbers. So let's display again the first image so we can see now the transformation applied. You can see all of the zeros, and now notice what before were pixels between 0 and 255, now they are 0.99 and 0.71 and 0.44. So we basically just squeezed all of those numbers. All right, So this is good. This is looking pretty awesome. We are almost ready. So here I have a function that is gonna create the pairs to train my model. Remember, I'm gonna go all the way up. The way this is gonna work, this is called a Siamese network, very important. Siamese, there are gonna be two heads, okay? The way this is gonna work is I need to generate a bunch of pairs. Positive pairs and negative pairs. Now a positive pair, I'm gonna call it whenever we have two images that are the same, to two number threes, that's a positive pair. And the label for that pair is going to be a very short distance, so 0. So I'm gonna give it, here is a 3 and a 3, and the distance must be 0. So do the computation, and at the end, the distance that you come up with all the way down here should be 0, okay? That neuron should be equal to 0. And if I pass two images that are different, let's say a 4 and a 9, I'm gonna give it a large distance. So I'm gonna give it a 1, okay? Assuming that 1 is as large as it's gonna get, I'm gonna say, hey, here is a 4 and a 7, that's a negative pair because they're not the same. 4 and a 7, and the label that you should be getting at the end, the output that you should be getting must be 1 or close to 1, okay? That is what I need to generate now, generate a data set of pairs. So how am I gonna do that? Very simple. I have a data set of samples, so I can get every sample, I have 60,000 of them. I can get every sample and then grab that image and then get a random image that represents the same digit, and that will be a positive pair. And I can get a random image that's a separate digit, a different digit, and that will be a negative pair. And then I can go to the next image and do the same. So if you do the math, if I have 60,000 images and for every image I generate two pairs, a positive one and a negative pair, I'm gonna end up with 120,000 pairs to train my model. So let's see how the code works. Just very, very simple. I have a couple of arrays here to just hold that information. I'm gonna go through all of my images in my data set. I'm gonna grab the digit representing that particular image. Let's say this is a number 5, just for gigs. And then I'm gonna find, with this random choice, I'm basically finding any other number 5s that are in my array. And then I'm grabbing one randomly. So I'm basically filtering my whole list of images saying, find me another number 5, okay? I'm gonna grab that index so I can just reference that image. I can add a pair saying, this is the original 5, this is the random one that we picked, that's the pair. And the distance, the y value, is going to be 0. Remember, if there's a positive pair, the distance must be 0. So there must not be any difference in those embeddings. And then I'm gonna do the same thing but with a negative pair. The only thing that changes now is number 1, instead of finding a digit that represents the same value, I'm gonna find a digit that represents a different value. So if I started with number 5, I'm gonna say, give me a random value, a random digit here in my data set that is not a number 5, okay? So it's gonna grab number 9, whatever it is, okay? I'm gonna add that, the original number 5, with a number 9 as a negative pair. And I know it's a negative pair because I'm gonna be adding the y value for this one here. It's just gonna be 1, indicating the distance should be the maximum value that we allow, which is number 1, okay? So by going through this, I'm gonna be getting the 120,000 pairs with all of the y values, okay? All right, so this function, after I go through that loop, the only thing that I'm doing here is shuffling that. So basically I'm rearranging all of the pairs so they don't look positive, negative, positive, negative, positive, negative. It's gonna be all messed up. So I'm gonna execute this function, and now I'm going to call that function to generate pairs for the training set and to generate pairs for the test set, okay? Now I had 60,000 images on my train set, therefore I'm getting 120,000 pairs. Now notice the dimensions here. I have 120,000 pairs. 2 is the second dimension, indicating there are 2 images, and each of those is gonna have 784. That's how you read this. So 120,000 elements, each of those with 2 images, each of those with 784 pixels. And then for the test, I had 10,000 images to test whatever model we're building. Therefore, now I'm gonna get twice as many pairs, okay? So now I have 20,000 pairs. Cool. So I built a quick function here. I'm not gonna go through the code. I promise there's nothing magic in this code. It's just, this function is gonna receive an array of pairs and it's gonna display the pairs. So in a fancy way, so we can take a look at how they look. So I'm gonna execute that. And what I'm doing is displaying 10 of the pairs, okay? So you can see the first one here is 1 and 1 and is positive pair because they are the same. Then I get another positive pair, 8 and 8, a negative pair, a 4 and a 7. So 4 and 7, they're different. Therefore, this is a negative pair. That's why it indicates here that it's negative. Then I get 0 and 8, and that's a negative. A 6 and a 4, that's a negative. 0 and 0 is a positive, and 2 and 2 is positive. You get the idea, okay? So those are random pairs that I got from my generation of pairs. Cool. Time to start building the network. This is where the magic is going to happen. This is the beauty of the whole thing, okay? I have the pairs, just need to build that network, train it, and see if it works. So let me go back up. And here you can see what that network will look like. I'm gonna start by creating those two inputs, defining the inputs that are gonna be expecting my pixels, okay? So very, very simple. If I go down here, I'm gonna be creating these two inputs here, okay? That's how you create an input in Keras. There is no magic here. Notice that the shape, you need to specify what is the shape that you're expecting. And I'm expecting 784 pixels, each of those two inputs. Input 1 is expecting the first image of the pair. Input 2 is expecting the second image of the pair. Beautiful. Next in line is the trunk, the twin, the network, the one that is going to do the work. Let's go back up really quick. This network here is going to have an output of 128 values. What does that mean? Well, that is the size of the embedding. By the way, if you know about the OpenAI embeddings, the one that they use when you're using ChatGPT, for example, those embeddings are 1,536. That's the size. That's how many coordinates are in one of these vectors. 50,536. Okay? That's a lot of numbers. In my particular case, just because this is a toy problem, I'm choosing to create a very small embedding of only 128. That is a value that you could explore whether or not 128 is the right size. It depends. And different problems are gonna need different sizes. You can go with 64, you can try with 56, you can try with any number that it occurs to you, okay? For this example, I'm just gonna generate them with 128. Now, because these are the embeddings, that will be the output layer of this network here, okay? The output layer of the network has to be those 128. So let's take a look at the code, what I did in there. All right, so I'm gonna be using the sequential API. This is a Keras API. When you're building just a model that's one layer after the other, I'm just using the sequential API. So I can specify, again, one after the other, the layers here. Now, this network, one of these networks, is going to expect on one side 784 pixels. So that's what's gonna be coming from the outside into this network. Then I have a couple of dense layers. A dense layer is a fully connected layer. Nothing fancy. Every neuron on one of these layers connects to every other neuron in the next layer. That's it. That's how a fully connected layer works. Why these sizes here? Because those are the numbers that I used. You could experiment with different numbers if you want to. Each one of these layers uses the nonlinearity ReLU, so that's the activation function that I'm using here. The second layer is 256, so it goes a little bit narrower. And then the final layer, this is my embedding. This final layer here, 128 pixels or 128 values, I have no activation function on this. I don't want to mess up with those values. I want the raw numbers. And those raw numbers, those are the coordinates. Those are my embeddings. Okay, so this is my network. Now, Notice that in my chart, I have that network twice. So the two inputs are pointing to that network there, okay? And they are twice here for representation purposes. Remember, I'm going to be sharing the weights like the node says. So let's see how I do that, okay? So I'm going to go down to where we define that network. And here is what I'm going to be doing. Pay attention to this. I'm creating twin one. By the way, I have to run all of this. I keep talking and not running code. Okay, so I have twin one, that's how I'm calling it, which is gonna be the top sort of like branch of my application here, my network. It's going to use the network that I just created, and I'm gonna be passing the input one to this network, okay? And twin number two is gonna use the same instance, and this is important, the same instance for input number two. So these weights are shared. So there are gonna be two twins, and these are twin one and twin two. I'm connecting this input one to twin one and input two to twin two, but the network is actually the same instance. Therefore, when we're doing back propagation and changing the weights, we're just doing that once because the weights are the same, okay? So I want to be clear that that's what's happening here. All right, so I have my two twins, and now what I'm missing, I have my two embeddings. Those are the outputs of the network. What I'm missing is the final layer. It's a one neuron layer, and that layer is supposed to represent, to compute the distance between my two embeddings. How do I do that? Well, fortunately, we can use what's called in Keras a lambda layer, which is basically a layer that is going to execute a function for you. So we are going to define what the function is that we want to execute. We're going to attach that lambda layer as the output of this beautiful thing that we created, and that's going to be our neural network. So let's see how we do that. Let's go back down. And sorry about the going up and down. It's a little bit dizzy sometimes, so doesn't matter. So here is my output layer. So forget about the function for a second. This is how I'm going to define my lambda layer. I'm calling it distance. That is the name of the layer. It's a lambda layer. Notice that lambda, I'm importing it here from keras.layers. And I'm passing the function that lambda layer will execute. And that function is the Euclidean distance that we're going to talk about in a second. And then I'm connecting this layer. I'm specifying what is the information coming from to this layer. I need to connect this layer with the stuff that comes before the layer. And those are my two twins. So I have an array, and the two twins are going to be coming into this layer. As you can see here, that's exactly what's happening. This top portion here is twin one, that's coming into this layer. This top portion here is twin two, that's coming into this layer. Okay? So let's go to the function, to the Euclidean function that is going to be doing the computation in this layer. What this function is receiving, we know, are the two embeddings, because that's what's feeding into the lambda layer. So these twins here, it's just basically the twin one output, or the embedding of the first image, and the twin two output, or the embedding of the second image. Now, what I'm doing in this line is unpacking this. So the computation here is clear. That's it. So I'm taking that twins, unpacking it into these two variables, and now I'm going to compute the distance between these two variables here. And the distance of two vectors we can compute using the norm of two vectors. It's also called the Euclidean distance. That's it. Simple function that we can call, saying just subtract the twin one output with the twin two output and just give me the norm of that. And that is going to give me how close we are, how close these two vectors are. That is the distance that I want to compute in that output layer. So the only thing left here on my network to finish the architecture of it is just putting it together, putting all of the pieces together. And the way you do that is just using a model class. So I'm going to get the model class. I'm going to specify, well, the inputs to this model are the two inputs that I created before, and the outputs to this model is just the distance function. That's it. Now, this model here is what you see in this diagram. Now we need to train it. To train it, we need to specify a couple things. So first, we need to specify what is the loss function that we are going to use. Second, we need to specify the optimization algorithm that we are going to use. We're not going to mess up with the optimization algorithm. We're going to use stochastic gradient descent or a variant of stochastic gradient descent. We're not going to worry about that. The loss function is what the beauty of this is. So remember that what we want is if these two images are different, like a 3 and a 7, and this distance is small, we want a loss function that returns a big value. So the updates are big. But if these two images are the same and the distance is large, we want the loss function to give us a big error, a big value. And the opposite. If the two images are the same and the distance is small, we want not to mess up with the weights. We want a loss function that recognizes that the network is working fine. That is what the loss function should do. And that is where we go to this paper here that is going to give us that contrastive learning loss function. It's called, let me find the name, the contrastive loss function. And the contrastive is you're contrasting something to something else. That's where the term comes from. All right, so I implemented bit by bit the same formula that you see here. Didn't make any changes. So let me show you how it works, or my implementation. Let's go down, and here is the contrastive loss. So this is a function, and it's going to receive, my function is going to receive a couple things, like any good regular loss function. It's going to give me the y true value, so what is the value that it should be, and what is the value that I got. Now, if you look at my diagram, I'm not going to pull it up here again, but the value, the output of my network is a single value, it's the distance, right? That's the distance that we're computing. And the y true value, the ground truth, the label of one pair is either 0 or 1. It's 0 if those images should be close together or are the same image, or 1 if the images are different. So those are the two values that I'm receiving here, the y value and the distance, okay? That's y and d. All right, so let's go to this line here and try to track it bit by bit with the paper. The paper says the loss function should be 1 minus the y divided by 2 times the square of the distance. That's the first term right there. 1 minus the y divided by 2 times the square of the distance. Bit by bit. Plus y divided by 2 plus y divided by 2 times the square, all of this is squared, so the square of the maximum of 0 and a margin minus the distance, and a margin minus the distance. Now that margin is a constant. The constant is just like a radius, and you have to read the paper to sort of like get the idea. It's not important here. I'm using 1 as the constant. You can see it here. I'm initializing that with 1. So not a big deal, but in short and in English, not in math terms, what this loss is going to do is if images are the same, but the distance is large, the loss is gonna be bigger. If images are large or different and the distance is short, the loss is gonna be big. If the images are the same and the distance is small, the loss is gonna be small. If the images are different and the distance is large, the loss is gonna be small. That is what the loss function is going to do. Now we need to set it up and we're ready for training. So this is how you set up this loss function. Let me execute that line. And you come here, by the way, I don't even know, no, I did not execute this line here. What's going on? Oh, I need to execute this, then need to execute this, then need to execute this, and now we get to the compilation process. So I need to compile my model so I can train it, and I'm gonna specify the loss is the function that I just created, this contrastive loss function. The optimizer is Atom. Atom is just a variant of stochastic gradient descent, a little bit more advanced, use Atom. And then the metrics that I'm going to use are I'm gonna use binary accuracy because, hey, listen, this is very simple to do with binary accuracy. I either get a pair correct or not. So if my distance is small enough, less than 0.5, and the images are the same, that's good. If the distance is large, greater than 0.5, and the images are the same, that's bad. That's basically what binary accuracy is gonna do for us. So after doing that, I'm actually gonna execute this. I'm gonna come back, but first let me start just training the model because it's gonna take a few minutes to train the model so you can see it working. So after compiling my model, I'm gonna plot it. So this utils here has a plot model function where you can see what the structure of the model looks like. And notice this looks almost the same to my diagram, except here the trunk, the network, the body of this neural network, it's represented only once. So we get the input layer, which is expecting 784 pixels, 2 input layers. So remember, it's a pair of images that I'm gonna be showing this network, each connected to one of these input layers. They both go to a sequential model, which is the simple neural network that we built. The input of that sequential model is 784. So it's gonna be grabbing one of these images, and the output is 128. That's our embedding. That's what we care about. And then this sequential model is feeding into the lambda function, which is receiving 2 embeddings, one for each image, right? And the output is 1 neuron, and that is the distance. So it's a value between 0, it's a small value. It's not even between 0 and 1, it's just gonna be a small value. That is the whole structure of my model here. Beautiful. So now it's time to train the model, to fit the model. So how do I do that? Well, in Keras, it's just very simple. So first, I need to pass the X values, so the training data. I need to pass the pair of images. So how do I select the pairs? Well, I'm gonna grab the training pairs, all of the values, so that's what the column means. So the first axis, which is the batch size, the number, the rows, just give me all of them, but only take 0, meaning the first image. Remember that if we go, well, now it's executing, so I can now show you, well, it's gonna end now. So I'm gonna show you here, I'm gonna just create a new code, just so you see here the shape of this, so it actually makes sense. Let it finish running. By the way, all of these run in my GPU. I'm gonna show you my activity monitor here. If we're lucky, you're gonna see the GPU here in 1 second. Well, it's already coming down. I should have done it before, but anyway, this is my GPU, what it looks like. You can see here the blue lines that are showing up. And that is, I just got it at the end of the training, but those, I'm pretty sure they got all the way up to 100% while it was training because it was using the GPU. You can see it now how it's coming down. Unfortunately, I only got the GPU, I only showed this by the end of training. Anyway, not important. Let's go back here. Let me show you the shape of this. So I have 120,000 pairs. So I'm saying, get all of the pairs, and from the other axis, only give me the first image on that axis. I have 2 images, so get all of the first pairs. So that is the first thing that I'm gonna pass, okay? Right here. And then for the second pair, just get all of them, but now get the second image. That's what this 1 indicates. So that's gonna get the second pair, okay? So that is my training data. Now, what is my labels, or what do they look like? Well, just get the Y pairs, which are values. If I go here, just grab all of them and everything else. So remember, if I get just one of these, you get like this is a 0, meaning that is a positive pair. If I get another one, maybe I'm lucky. Well, I just got the same one, but maybe I'm lucky and I get, yeah, there we go. This is a negative pair, it's a 1. So that is what I'm passing as the X and the Y. Let me just remove this. The validation data I'm passing is the same thing. I'm passing using the same structure. I'm passing the pairs from the test set. That's it. So it can actually validate this thing. Then I'm using a batch size of 32. So that means that during every iteration, the model is going to be taking 32 pairs, running them through my network in order to compute the distance at the end and compute the loss function. Okay, 32 at the same time. You could experiment with this number, with 64, with, I don't know, maybe 8, whatever the numbers is, and see if you can get better results. I just use 32 is fine. And I'm gonna do this for 5 times, 5 epochs. Now, here is the result of my training. Let's try to understand what's happening here. First, you get this weird number, 3750. Well, remember that I told you I'm using a 32 batches at the same time. So if I have 120,000 images divided by 32, that means that every one of those have to go through 3750 times. That's the number that you see here, right? It's the number of samples divided by your batch size. That's how many times we're gonna go through, how many iterations we're gonna run, okay? So during the first epoch, that's what we did. It took 33 seconds. The binary accuracy during the first pass was 89%. That was the training accuracy. Then the loss was this. What's really important here, the validation accuracy was 96% and the loss was 0.01. What's important here is just to see this accuracy that's going up. As you can see, 98, 99, that's cool. And the validation accuracy is also going up. It sort of like stabilizes here, so it doesn't go up after that. That's fine. I have a plotting here that's gonna show us. So for my 5 epochs, you see the training accuracy going down, the validation accuracy going down a little bit as well. I might, you might want to train this maybe another epoch or so and see if that makes it better. So now let's do the evaluation. So for the evaluation, the interesting thing comes now, I promise. For the evaluation, I'm just gonna use the test pairs, same format that you saw, and I'm just using the predict on my model, on my Siamese network. I'm using the predict function, and then I'm gonna be displaying the pairs, and I'm gonna be passing another parameter to the pairs, so it displays this beautiful green or red if it makes a mistake. So let's see what we got here. All right, so I run all of the test data, and it's when I pass a 7 and a 7, the model is telling me, yeah, they are the same. I pass a 5 and a 5, it's the same. Let's find one that's different. I passed an 8 and a 9, and the model set is the same. It's different. The green color means it did not make a mistake. You can get it to make mistakes, so there are mistakes. You're gonna see now that I compute the accuracy right here, and the accuracy is 97%. So there are certain mistakes where the model thinks they're the same, but they're actually different. But it's pretty cool. It's pretty darn good by doing it like that. This is using the Siamese network with a pair of images. But what I really wanted to do is just get the embeddings, because now I can do interesting stuff with the embeddings. So here is the trick, not the trick, but here you can see I'm displaying the list of layers of my Siamese network. And no surprise, there is one input layer here. There is another input layer here. Then there is the sequential model. Remember, we have 2 input layers. There is the sequential model, and there is the lambda function. Those are the 4 components that make up the Siamese network. The embeddings are this sequential model. So this sequential model, the output of this sequential model are the embeddings that we care about. So I'm going to grab that sequential model. I'm gonna say my embedding model is the third layer. So 0, 1, 2. The third layer of my big model, that is gonna be my embedding model. And now I can use that embedding model. Just a portion, I'm getting a section of the big Siamese network, a section just to generate embeddings, okay? I don't care about passing pairs. I just care giving an image, just give me the embedding of it. All right, so let's see if this works. So this code here is basically selecting 3 images. And notice that the first image, the image represented by index 1, is a random image that represents number 3. The second image is a random image that represents number 3. And this is me just testing this out, okay? So index 1 and index 2, they both represent the digit 3. And then index 3 represents digit 7, okay? So these are the indices. Okay, so awesome, beautiful. Well, actually, I re-execute that and I got new values. So these are the indices. Now I can use my embedding model to generate embeddings for those indices. So look at this. Embedding 1 will be my embedding model dot predict. And I'm gonna pass the image represented by that specific index. So I'm going to generate embeddings for all 3 indices. Now this reshape here is just because I need to create the format that the embedding model is expecting. There's nothing fancy here. I'm just changing how the structure of the arrays look like. So I'm going to execute this, and now I have 3 embeddings that I generated with my model. After creating these 3 embeddings, I can now compute how far away they are. So in this particular case, I'm going to compute the distance between embedding number 1 and embedding number 2. And you can see that the distance is 0.13, almost 0. It's very close to 0 because embedding 1 represents number 3 and embedding 2 represents number 3. And if I do the same thing, oh, by the way, this is the old code. So if I execute this, it's 0.04, even smaller. If I do the same thing now with embedding 1 and embedding 3, so that's a 3 and a 7. So this distance here should be large, and embedding 2 and embedding 3 should be large. Let's execute this. And now you can see a 0.99, meaning those 2 numbers are very far apart, and 0.98. Those 2 numbers are very far apart. So hopefully this gives you an idea of how to use these embeddings. There are a bunch of applications for anomaly detection, again, for RAG systems if you wanted to. And obviously your large language models are not using such simple embeddings. They're way more complex embeddings. They're trying to sort of like condense the knowledge in the world into these multi-dimensional vectors. But hopefully this small neural network gives you a better understanding of how you can create and use these embeddings. And I'll see you in the next one. Bye.